You know when you're downloading a huge file or streaming a movie and it just works? Every single piece arrives perfectly, in order, without a single bit missing. Have you ever stopped to think about how incredible that is? I mean, the internet itself is a total mess. It's this chaotic, unpredictable wild west of networks. Well, behind the scenes, there's this master conductor, a protocol that creates perfect order from all that chaos. So today, we're going to pull back the curtain on the Transmission Control Protocol, or TCP, the unsung hero that really makes our digital world reliable. So, here's our game plan. First, we're going to dive into what I'm calling the Wild West of the Internet to really get a feel for the problem TCP was built to solve. Then, we'll meet our hero, TCP itself, and see how it brings order to all that chaos. We'll peek inside its toolkit of really clever tricks, and then we'll see how it learned to play fair with everyone else on the network. And finally, we'll put our knowledge to the test and solve a few challenges to see these ideas in action. All right, let's get into it. Section 1, the Internet's Wild West. You see, before you can really appreciate TCP, you have to understand the world it operates in. And let me tell you, it is not some neat and tidy superhighway. It's messy, it's unpredictable, and honestly, by its very design, it is fundamentally unreliable. I mean, really think about this for a second. When you ask for a file, it gets sharded into thousands of tiny little pieces we call packets. Now, these packets don't travel together in a nice, orderly convoy. Oh no. Each one gets sent out on its own crazy adventure, navigated independently by routers all over the globe. So one packet might zip through a super fast fiber optic cable in London, while another gets totally stuck in traffic on some slow coffee shop Wi-Fi in Seattle. Routers can even just drop packets on the floor if they get too busy. So your data can get lost, it can show up twice, or it can arrive completely out of order. How on earth does that file on your computer end up perfect? Well, that is the exact problem TCP was invented to solve. And this brings us to this key idea of an internetwork. See, the internet isn't just one big single network. It's a network of networks. And each one has its own rules, its own layout or topology, its own speed limit or bandwidth, its own regulations on how big a packet can be. You've got high-speed fiber that's like a Ferrari, but you've also got old copper lines that are more like a bicycle, and maybe even a laggy satellite link that's like a rowboat. TCP's job is to be the world's best logistics manager, making sure the entire package arrives safe and sound, no matter how wild and different the journey was for each individual piece. So how do you tame this digital Wild West? Well, you call in a hero. And that brings us to the star of our show, the Transmission Control Protocol, TCP. This one sentence is basically TCP's entire mission statement, and every word here is important. Reliable means you get your data and you get it right. No corruption, no missing pieces. End-to-end is crucial. It means this guarantee of reliability is made between the two computers talking to each other, not by all the messy networks in the middle. And byte stream. That just means that to your web browser or your email app, the data looks like a smooth, continuous flow, kind of like water coming out of a tap. It completely hides the fact that underneath it's all being stitched together from thousands of individual packets. And these are the core principles that make it all happen. Full duplex, that's just like a phone call. Both people can talk and listen at the same time. Point to point means it's a private conversation, just between two computers, not a giant broadcast. And then you have its superpowers, dynamically adaptive and robust. TCP is constantly feeling out the network, checking its pulse, and adjusting its speed to avoid causing traffic jams. And it's tough, built to handle all sorts of unexpected failures. It's this powerful combo that has made TCP the absolute workhorse of the internet for decades. Okay, so we've covered the what and the why. Now it's time for the really cool part, the how. Let's pop the hood, open up TCP's toolkit, and look at the actual mechanisms that make all this reliability possible. This right here is the absolute bedrock of TCP's reliability. Imagine you're trying to send a 1,000-page novel to a friend, but you have to send it one page at a time through the mail. Well, if you number every single page, your friend can easily put the story back together in the right order, even if the pages arrive all mixed up. The acknowledgement number is just your friend calling you up and saying, hey, I've got everything up to page 50, now I'm waiting for page 51. If you don't get that call about page 51 after a little while, you just assume it got lost and you pop another copy in the mail. It's such a simple idea, but it's incredibly powerful. I mean, the difference is just night and day. Without these numbers, you get digital garbage, a corrupted file, a scrambled web page. But with them, TCP acts like this super meticulous librarian, carefully putting every single packet on the shelf in its correct place, and then politely asking the sender for a new copy of anything that went missing. Now, here's a really fascinating safety feature. When a TCP connection is over, it doesn't just hang up right away. One side enters this weird state called the time-wait state. The best analogy is a restaurant. After a party leaves the table, the staff waits a couple of minutes to clean up and make sure nobody left a phone behind before they seat the next group. This pause is mandatory, and it exists for a very, very good reason. So why is this wait so critical? Well, it's because a few packets from the old conversation might have taken a long, scenic route through the internet. They're like zombie packets. The time wait period is a buffer. It's like a firewall in time. It gives those zombie packets a chance to finally arrive and be discarded before a brand new conversation can start using those same identifiers. Without it, a zombie packet from your old bank transaction could wander into a new video call, causing all sorts of bizarre confusion. Okay, so TCP is amazing at managing its own connection, but here's the thing. It doesn't live in a bubble. It has to share the internet with millions, even billions of other connections. So to stop the whole internet from grinding to a halt, TCP has this built-in social contract, a set of rules for playing fair. We call this congestion control. And this is that dance in action. It's called AMD. Imagine two users who are both trying to download a file. They both start by gently increasing their speed, kind of probing for more capacity. That's the additive increase. But as soon as the network gets too crowded and a packet gets dropped, they both take a huge step back, slamming on the brakes and cutting their speed way down. That's the multiplicative decrease. Then they do it all over again. Gently step up, big step back. And over time, this cooperative dance naturally pushes them toward that fairness line, where they end up sharing the network's bandwidth in a really efficient and fair way. So the algorithm itself, additive increase, multiplicative decrease, or AMID, is beautiful in its simplicity. The strategy is basically increase cautiously, decrease aggressively. The increase is additive because it's a careful, optimistic probe for just a little more bandwidth. But the decrease is multiplicative because when trouble hits, you need a powerful, immediate reaction to ease the pressure on the network for everybody. And it's this incredibly simple, conservative behavior happening millions of times a second across the globe that keeps the internet from collapsing. It's a truly amazing example of cooperative control without a central controller. All right, we've gone through a lot of the theory behind reliability and fairness, but now let's make it real. Let's get our hands dirty and walk through a few quick challenges to see exactly how these concepts work in the real world and how all these moving parts fit together. Okay, first challenge. This one is all about how the different network layers stack on top of each other. So let's define our terms real quick. The payload is your actual data, the text of your email, right? The header is the control info that TCP slaps on, like an envelope with addresses and those sequence numbers. The whole TCP segment, header plus payload, has to be carried by the layer underneath it, the network layer. So what's the total size the network layer needs to be able to carry? The key here is just to remember how encapsulation works. The network layer's payload isn't just your data. No, it's the entire TCP segment, your data and TCP's header. So all we have to do is add the 1,450 bytes of your data to the 20 bytes of the TCP header. That gives us a grand total of 1,470 bytes for the network layer payload. It's like putting a 1,450-gram letter inside a 20-gram envelope. The mail carrier has to carry the whole 1,470 grams. Simple as that. Okay, next up, let's put that AMID algorithm into practice. We've got a connection that starts at a certain speed, it successfully ramps up a few times, and then bam, it hits some congestion. Let's figure out what its new sending rate will be. Let's walk through the math here. We start at a nice, safe 1 megabit per second. We then have 4 successful increases, and each one adds half a megabit. So 4 times a half is 2. We add that 2 Mbps to our starting rate of 1, which gets us up to a speedy 3 Mbps. But then, packet loss, congestion. The algorithm instantly kicks in with that multiplicative decrease. We take our current rate, 3 Mbps, and multiply it by the factor of 0.5, which just cuts it in half. So our new, safer sending rate becomes 1.5 Mbps. See, cautious increase, aggressive decrease, right there in the numbers. All right. For our final challenge, let's do a quick conceptual check. We're going to circle back to that super important safety feature we talked about, the time-wait state. Let's recap. Why exactly does TCP have this mandatory cooldown period after a conversation ends? And the answer is, it all comes back to killing those zombie packets. The time-wait state is that mandatory quiet period that makes sure any old, straggling packets from the last conversation have died off before a new one can start. It's the digital cleanup crew, making sure the channel is perfectly clean before it gets used again, preventing total chaos. And that really brings us to the end of our deep dive into the magic of TCP. It's this incredible protocol that's willing to trade just a little bit of overhead for a massive amount of reliability and fairness, which is exactly what things like email and web pages need to work. But that does raise one final, really interesting question. What about things like live video streaming or online gaming? Places where a tiny delay is sometimes way worse than one lost packet? What do we do when we need pure, unadulterated speed above all else? Well, that's a whole other story for another explainer.